This segment we're going to talk about dehumidification. In the previous segment, we talked about simple heating and cooling, and we said that if we cooled atmospheric air at constant pressure, as long as we didn't cool below the dew point temperature, so we're at or above the dew point temperature, we won't see any condensation. But what if we cool below the dew point temperature? Well, in that case, of course, we do have condensation. So what we're going to do is we're going to look at the behavior of the saturated water vapor as it moves through the duct, because that's the portion of that two-phase mixture that's a result of that condensation. That's the part of that two-phase mixture that's still part of that atmospheric air. It still exists as a gas. Now there is a saturated liquid portion, and that's exiting as a saturated liquid or condensate at the very top right-hand corner of that little picture. It's exiting at the bottom. So let's look at that saturated water vapor, and of course it's going to move along a line of saturated water vapor. So it's going to move along the saturated water vapor line, and it's going to end at T2. And you'll notice that the pressure at state, or the partial pressure at state 1 and 2 are no longer equal to one another. So PV1 and PV2 are not equal to one another, and the reason is because as condensation occurs, the mole fraction of that water vapor is going to, of course, decrease because there's less water vapor. You have a condensation reaction or condensation process, and you've got condensate leaving. So the amount of water within that atmospheric air is decreasing. If I multiply both sides by pressure, and I could just replace that with P2 and P1 because they're equal to one another, that's the overall pressure, then what I see is that the partial pressure of my water vapor at state 2 is less than that at state 1. The other thing that I do want you to make note of is on the diagram in the upper right hand corner, you'll see that the relative humidity is 100% at the end of that dehumidification or condensation process because you're right on that saturated vapor line. And the other thing to note is that your specific humidity has, of course, decreased. All right, so let's look at how we can mathematically model this. The first thing we're going to do is apply our conservation of mass. We're going to do it to both components, the dry air and the water vapor, or dry air and the water. So for the dry air, we've got things are occurring at steady state. So you've got one inlet, one outlet. So m dot A1 and m dot A2, which you see now on the diagram at the top right-hand corner. Those are equal to one another. You could just call that m dot A. Now let's look at the water. So here you have the case where you've got one inlet, but you have two outlets for the water because you have saturated water leaving at the very bottom of my diagram, being drained out of there. So that's your condensate. So when you apply your conservation of mass, you'll see that the sum of the m dots coming in equal the sum of the m dots going out. I've only got one thing coming in, but I've got m dot V coming out plus m dot W coming out. That's my condensate. And I can rearrange this to define m dot W, and I'm going to rearrange this further. It's going to look a little bit uglier, but the reason I'm going to try to isolate m dot A on the outside of this is because I can put those terms in the middle of those parentheses in terms of the specific humidity, because the specific humidity is its mass of the vapor over the mass of the air, and you could also put that in terms of the mass flow rate of the vapor over the mass flow rate of the air. Now I'm going to apply my energy balance. So it's an open system. Here's my open system form of the first law. Lots of things are going to cancel out. Q dot is not going to cancel out because the way that I've drawn my boundary here, I'm capturing the fact that heat is being removed from that system by some means. In this picture, it's being removed by means of a cooling coil. All right, so I've got Q dot equals the sum of the m dot H's coming out minus that coming in. And I've got a couple of terms here. So I've got the dry air, stuff coming out minus stuff coming in. I've got the water vapor, stuff coming out minus stuff coming in. But I've also got that condensate, that's coming in. So now what I'm going to do is I'm going to isolate the mass flow rate of the dry air. So m dot A2 and m dot A1 are equal to one another. So for that first term, I can take m dot A out of the parentheses. I'm not quite ready to do anything with that second parentheses term, but this third parentheses term, I can look back at my mass balance and see that I did use the conservation of mass to define m dot w, and so I'm just going to put it in my energy balance here, and that gives me an m dot a term that I can do something with. And the something that I'm going to do with it is just divide the entire equation by m dot a, and that'll give us units of kilojoules per kilogram of dry air passing through that atmosphere, passing through that duct. So that first term, of course, we don't have an m dot a, that's got divided out. The second term, I'm just going to write it, kind of distribute out that 1 divided by m dot a, and of course the m dot a disappears from that third term. And then I recognize m dot v over m dot a as just the specific humidity. And then if I rearrange this just a little bit more, at least those two parentheses at the beginning, I can get things in terms of, and let's move that up, I can get that in terms of the specific enthalpy of the moist air at state 2 minus the specific enthalpy of the moist air at state 1. And those are things that I can look up on my psychrometric chart if I'm at 1 atm, and I can use that psychrometric chart. There's one thing that I kind of left out here and I didn't mention, but that temperature of the saturated water of the condensate that's leaving, that's being drained out at the bottom, that's coming out at the same temperature as the atmospheric air, because you've got this two-phase mixture, right? So your temperature of the saturated liquid and the saturated vapor should be equal to one another. So when you calculate what HW is, you can approximate that as H sub F at TW, which is equal to T2. Okay, well, I hope that was helpful. Thank you for watching. We'll work some problems the next time we meet.